installment of the first lecture. Today we're going to learn some tools for reducing the complexity of complex reaction networks. We're going to start pretty simple with the pseudo-steady state approximation. We're going to talk about the quasi-equilibrium approximation, and we're also going to visit the rate-determining step approximation. So these often can be used to turn a very complex reaction network into a rather manageable set of equations that you can use to derive a rate law, and in many cases they work quite well. So the first example that we're going to start with is this series reaction where species A converts with rate constant K1 into species B, and then B goes on and converts with rate constant K2 into species C. The case that we're going to look at in particular is this case where K2 is much larger than K1, and so the qualitative thinking is that once in a while you make a B molecule, and then rather rapidly that B molecule is consumed again and should not have much of an opportunity to build up a significant concentration of B in the system. Okay, so you can exactly solve this set of rate equations for a constant volume batch reactor. You get that the concentration of A is this exponentially declining function of time, and that the concentration of B initially rises and then it as well declines a long time. Okay, so this is an exact solution, and what we're going to do with this is kind of justify the pseudo-steady state approximation by going through and making a series of approximations and explaining why they should work. So the first step is this singular perturbation step, right? So we have a small parameter in here, that's K1 over K2 is a small parameter, and you see that in the exact solution it's added to a number of order 1, and so we can really drop that off. And the one case where we don't want to get rid of it is right here. When it's the leading singular term, then dropping it off would mean that we're approximating that B is actually equal to 0. Okay, so we don't want to do anything that drastic. Keep this particular occurrence of K1 over K2 and let all of the rest of them go. And that gives us this equation for the concentration of species B. And if you plot this versus the exact solution, you will see that this approximation is actually extremely accurate, at least order K1 over K2 accurate over the entire course of time. But in the pseudo-steady state approximation, we're going to make one more approximation on top of this singular perturbation, and that is to say that we really only care about the solution after that fast initial time where B, this term, is gone at least. And then you look back to the concentration of species A and you realize that this just says that B is a multiple K1 over K2 times A. Now, if you look at that particular expression for B, you realize that we could have arrived at this expression by another route, right? We could have said that the rate of formation of B is approximately equal to 0, okay? And then that would have given us this equation, which if we solved it would reduce to this quantity, okay? So now this is really a shortcut to these kinds of things, and it's important to realize that you're making two approximations here. You're getting rid of a small parameter, and you are also assuming that you only care about things after this very short time, okay? So in the pseudo-steady state approximation, you're replacing a time-dependent quantity B with its own differential equations that govern that quantity with algebraic equations that relate B as a function of time to other species in the reaction network, typically reactants, products, and abundant intermediates. Solution looks like, so this is the exact solution plotted as solid curves here. This is the concentration of A, declining exponentially over time, and the concentration of C after a very short transient time. It sort of looks like a exponential decay towards some plateau value. And then there's this concentration of B over A, so this has been non-dimensionalized. And notice here that this thing comes up and then comes back down. If you zoom in, you can see that behavior very, very well. So this starts at 0. There's initially no B in the system, and that increases over time and then starts to decline, right? So this is the pseudo-steady state approximation in dotted lines here, and you see that after a time on the order of 1 over K2, that the pseudo-steady state approximation does a pretty good job of describing the exact solution. All right, so one last little note on this is that chemistry texts often write derivatives with respect to time of the concentrations of the species. And you know, in principle, this works in exactly the same way, and certainly we can apply this in situations where we are talking about concentrations changing as a function of time. But this does create some confusion because, of course, what you get out of this approximation is a statement that B depends on time, which seems like a contradiction, and also this creates maybe a perception that this pseudo-steady state approximation only works in batch reactor situations, and that's definitely not true. This thing can be applied in all kinds of situations, and we will do that a lot throughout the class. So when do you use the pseudo-steady state approximation? Well, it's useful anytime you have intermediates whose separate rates of consumption, that is the forward and backward rates leaving the intermediate state, have to both be larger than the net rate of generation of that species. The main requirement when you have a standard chemical reaction with some intermediates. There's another situation where you can use the pseudo-steady state approximation, and that is when you think about catalytic processes. And you can use the pseudo-steady state approximation as long as the catalyst concentration is much, much lower than the reactant and product and major intermediates concentrations. Okay, so when I say major intermediates here, I don't mean the catalytic intermediates. I mean things that might desorb and go back out into solution temporarily and then come back on. Okay, so you can apply the pseudo-steady state approximation to all catalytic intermediates in this particular situation. And the reason, if you want to think about it qualitatively, is that you have a large pool of reactants and products, and the catalyst is turning over many, many, many times before that concentration in the reactant reservoir changes significantly, right? So when you have this situation, you really can get away with the pseudo-steady state approximation for entirely different reasons, even when this isn't necessarily true for the individual catalytic intermediates. And the third requirement is that if you're applying the pseudo-steady state approximation, you should not be making conclusions about the very short time behavior. It does not describe those parts of the process correctly. So how to use the pseudo-steady state approximation? These are some guidelines that have been given in the excellent book by Frederick Helfrich. There's just three guidelines here that are useful to keep in mind. If you use the pseudo-steady state approximation on a species B, you should use the equation that arises from that approximation to eliminate species B, not some other species for which you are not making a pseudo-steady state approximation. Okay, doing the latter can lead to a disaster where you equate small numbers to each other, and they can be small to varying degrees, and this is not for getting good results. Okay, so the pseudo-steady state approximation is easiest to apply in a series of reactions if you start at the end and work backwards towards the beginning. Okay, so that just simplifies the algebra, so that's a useful thing to keep in mind. The overall rate laws that apply, that emerge from the pseudo-steady state approximation, can usually be written in 1+ form, and that's useful because it minimizes the number of independent kinetic parameters that you have to fit in the rate law when you go back and you compare to experimental data. So this is an example taken from Helfrich's book. So this is aromatic nitration, and what we're going to do is we're going to basically track the progress of the nitrate group from nitric acid all the way through until the aromatic ring is nitrated, and it goes through a number of intermediates that are labeled here X0, X1, X2, X3, and X4 out to the end, and there is an acid here that plays a role at the beginning and again at the end. Okay, so the net reaction is that we start out with an aromatic compound and a nitric acid molecule, and we end up with a nitrated aromatic ring and a water molecule free. Okay, so we're going to let the rate constants in this network be Kij, and that indicates the rate constant for going from Xi to Xj. Now, one little note here, this represents a complex reaction, but each of the individual steps depicted here are elementary steps. So we're going to be able to write down the individual rates for all of these individual steps in terms of mass action rate laws. Okay, so let's go ahead and get started with that. So the overall rate, we can come out here to the end. If we're interested in making this aromatic compound, then the overall rate is the rate of this last step. Okay, so doing that gives me this expression, and now I can plug this expression back into my rate law, and we get a new rate law that looks like this. It's K23 times the intermediate 2 kinetic constant. These are actually groups of kinetic rate parameters, And so this is this 1 plus form, right? So you see 1 plus a denominator that has a leading coefficient here, and all of these things end up being dimensionless. All right, so the other approximation that we will use quite frequently throughout the exercises and examples from the course is the quasi-equilibrium approximation. And many, many times you find reaction networks where this is quite useful. Reaction rates can vary over many orders of magnitude, and it's quite common that you have some slow processes and some extremely fast processes. And when those fast processes are reversible, then that's where the quasi-equilibrium approximation becomes useful. Okay, so this is, again, like the pseudo-steady state approximation, it's going to replace the rate equation with an algebraic equation. But the algebraic equations that you get out of the quasi-equilibrium approximation are typically much, much simpler than those from pseudo-steady state approximations. It requires that you consider carefully the equilibration and subsystem escape times to justify this approximation. And so let's talk a little bit about that. So suppose you have this complicated rate network, and I'm only showing this little zoom in on the interconversion between two species in that network, A and B. Okay, so this could be an isomerization. It could also be something like a discrete master equation where you have two states that rapidly interconvert with each other. Okay, so we've got a forward rate and we've got a backward rate, and the time that it takes to equilibrate these two, if you recall from your basic kinetics, is the sum of the two rate constants, and then you invert that quantity, and that gives you a time scale for equilibration. Now we can compare that to the time scale to actually escape this little subsystem of A and B once these two things are equilibrated, right? So that time scale, let's think about the subsystem A and B as A comma B, and I'm going to write down some new quantities here that probably are pretty unconventional, but that's the fraction of the time that the subsystem spends in A, and that's the fraction of the time that the subsystem spends in B. So I've written them as given mole fractions given that you're in A and B in this way, right? So this is now the time. What we're concerned with is the time to escape from this merged basin A and B, and that's going to be the sum over all the rates leaving state A and going somewhere other than B, multiplied by the fraction of time at equilibrium that you spend in A, plus the fraction of time in the subsystem that you spend in B, multiplied by all the rates leaving B and going somewhere other than A. So then you take the inverse of that, and you now have the escape time. Now, if the equilibration time is much, much shorter than the escape time, then you will have plenty of time to equilibrate once you found your way into this basin, and you can apply the quasi-equilibrium approximation to this little pair of species in your reaction network. Of course, this approximation is a bit harder to justify for bimolecular steps, and for those we usually just go ahead and apply it and then go back at the end and look at the concentrations and the rate law that you get and check to see whether the assumptions are consistent with those rates being much faster than the rates of the surrounding steps. So it's really quite easy for these first order reaction steps though. All right, so the couple things to note about the quasi-equilibrium approximation is that we can use this even when the overall reaction network outside of these two is not anywhere close to being in equilibrium. Okay, so the last approximation that we want to talk about is the rate determining step approximation. This is frequently described in terms of identifying a slow step of the reaction. Well, that actually doesn't always make sense. You know, do we have a slow step? At steady state, at least, all the steps must have the same net rate, and so it doesn't really quite make sense to talk about one of them being slow. But what we can do is we can look at the forward and the backward rates again separately, and what happens in cases where you have a rate determining step is that the forward and the backward rates all give you the same net rate. As you can see, this little gap is the same in all four of the steps in this reaction. But in this case, the forward and backward rates are quite comparable to the net rate, and in the rest of the cases, the forward and backward rates are much, much larger, right? So this is the situation where you would identify this as a rate determining step for the overall process. It's important to recognize that these forward and backward rates are not rate constants. They are the actual rate. Their relative magnitudes will depend on the conditions, the temperature and the concentration. And if you change the concentration, you can change the rate determining step, and if you change the temperature, you can also change the rate determining step, right? So this one would occur if you have two steps that are somewhat competitive with each other and they have different reaction orders. This one would occur if you have two steps that are somewhat competitive with each other and they have different activation energies. And in terms of differences between rates, but quite often what we're going to do is to start with free energy profiles obtained, for example, from ab initio calculations. In those cases, it's actually quite easy to spot the rate determining step on the free energy profile. So let's talk about how you do that. So you can plot this is a depiction of a free energy profile here with barriers and intermediates of different depths and sizes. You can imagine water pouring in to this landscape and looking at where the water is going to be held up, and that point where you have the deepest pool. So this one is the rate determining step. I've written slow step here, but you want to be careful with that terminology. The consequences of having a rate determining step is that these species down here, these states end up interconverting quite frequently, and so these are fast steps before the slow step, and these things come to a quasi-equilibrium. The most abundant species in this network, most abundant intermediate, is going to be this one right here at the deepest point in this pool, and that the effective free energy barrier, the one that you would observe experimentally, is the free energy to go from the rate determining step back to that most abundant intermediate concentration. And there's a lot has been written on these. In fact, in the engineering book that I referenced, Boudard has spent a lot of time developing theorems for working through these things and recognizing situations where you can apply the rate determining step and the quasi-equilibrium approximation and very rapidly simplify these things into rate laws. That there's really a hierarchy of rate laws, and what I showed you, the sequence that I showed you, was an increasing level of approximation in going from first, you have rate laws where you make no approximation, and sometimes that's necessary in cases like combustion kinetics. And then as you move towards approximate rate laws, you have pseudo-steady state approximations, and these, in principle, give you pretty accurate rate laws as long as you don't have things like branching steps. Then you can move to a more drastic approximation, and you get steps where you can make a quasi-equilibrium approximation. And then even more drastic approximation is assuming a rate determining step, which implies a lot of the steps that come before it are quasi-equilibrated. So this is sort of most general to less general, and also, so why would we do this, right? Why would we make these drastic approximations? Well, because this approximation is the one that gets rid of the most parameters in your rate equations, right? So as you move towards the center of this diagram, you're getting simpler and simpler rate laws, and those are easier and easier to compare to the experiments. Okay, so I think that is it for this lecture.